Good day everyone, we are the engineer. This is our final presentation of our project which revolves around Putra gas pipeline disaster. Our group members are the engineer, Yasewan, Lijini, Hazrul Shah bin Shahmin, and me myself. After the pipeline explosion occurred in Putra, Subang Jaya. The accident caused over 150 injuries and forced hundreds of residents to move away from their home. It was later confirmed that the explosion was due to gas leak in the underground peninsular gas utilization pipeline operated by TDLAS. Our objective is to propose and explain a multi-layered optoelectronic system that can both detect and mitigate similar gas pipeline disaster. Diving deeper into this disaster, the disaster occurred at exactly 8:08 a.m. The rupture happened between gate valve 210 and 211 of the PGU pipeline. The explosion produced flames nearly 30 meters high and generated temperature exceeding 1000 degrees Celsius. A total of 150 individuals were injured, many with severe burns. Around 500 residents were displaced. 237 homes were damaged and nearly 400 vehicles were affected. One critical issue was that the lack of an early warning system. Gas had leaked and accumulated unnoticed until it ignited. By then, it was too late to prevent the explosion. Next, let's take a look at the gas and explosion itself. Natural gas, particularly methane or CH4, is the primary component used in pipelines. While efficient for energy, it is invincible, odorless, and highly flammable, which makes it a silent threat. The risk escalates when methane leaks underground and mixes with air. If the mixture reaches a concentration between 5 to 15%, it becomes explosive. A simple spark or heat source could provide the activation energy needed to trigger a combustion reaction. This reaction is exothermic. It releases a lot of energy, causing a chain explosion and fireball. The fact that methane is undetectable by human and pipeline are buried makes leak detection very difficult. This is why real-time sensing and automated intervention are so important. Thank you.
In this project, we focus on two powerful sensing technologies, distributed acoustic sensing and distributed temperature sensing. DAS turns fiber optic cables into thousands of virtual microphones. It detects vibration or sound changes along pipeline, useful for identifying leaks, equipment failure, or tampering. TTS uses the same fiber to measure temperature along its entire length. It detects heat build-up, fire risk, or gas leak based on thermal change. Both systems offer continuous real-time monitoring over long distance. Here's how DAS works. A laser pulse is sent through the fiber optic cable. As sound vibration hit the cable, some light is reflected back. The system analyzes this light to detect abnormal acoustic signal, like a leak, pressure wave, or digging. DTS works similarly. The same fiber detects temperature change by analyzing how the light scatters due to heat. The system then maps the temperature along the pipeline. Both DAS and DTS send real-time alert when something unusual happens. This helps operators act fast before an incident becomes a disaster. Let's connect this to the Putra gas explosion. If DTS has been installed, it could have detect rising temperature near the gas leak, allowing preventive action. DAS could have picked up vibration or pressure anomalies before the explosion. This incident shows why smart fiber sensing is so important. By combining DAS and DTS, we can improve safety, reduce risk, and respond faster in gas pipeline emergency.
This slide introduces the tunable diode laser absorption spectroscopy, or we can say TDLAS. It is a laser-based technology that detects the gas like the methane using a precise 1.65 micrometer laser tuned to the methane's absorption line. It offers high sensitivity, fast response, and accurate gas detection. To improve the safety and the efficiency, the TDLAS sensor is mounted on a drone. These devices allow for remote gas leak detection in the hazardous and hard-to-reach areas, such as the Putra height, without putting responders at the risk. The drone also provides a real-time GPS tag data, supporting faster emergency decision-making and reduce the response time during the incidents. This slide shows the architecture of a drone-mounted TDLAS sensor for the methane detection. The core is the laser and moderation unit, where a TDL operating at 1.65 micrometer targets the methane absorption line, a laser driver, temperature controller, and a moderation circuit to ensure the wavelength stability and enable the sensitive detection through a wavelength moderation spectroscopy. An optical system shapes and directs the beam using a collimating optics and a multi-pass gas cell. A micro pump pulls in the air to increase the interaction path length for the better sensitivity. The beam then reaches the detection and signal processing unit, where an indium gallium arsenide photodetector captures the transmitted light. A load-in amplifier and DSP extract the methane's 2F harmonic and concentration is calculated using the Beer-Lambert law. The data and communication handles the GPS tagging, real-time wireless transmission, and onboard data storage. Finally, the system is powered by the drone's battery, enclosed in the rugged and weather-resistant housing for the stable field operations. Drones equipped with the TDLAS offer a fast, safe, and highly accurate method of detecting the gas leaks. They can operate in the hazardous areas without risking the human life, quickly scan the large or hard-to-reach areas, and detect the methane down to the ppm levels. With the real-time GPS tag data, they help the responders visualize the leak location and take the quick action. And in addition, TDLAS operate reliably even in the tough urban or the weather condition. All of these help prevent a secondary explosion and speed up the emergency response. In response to the methane leak at the Putra Heights, a drone equipped with the TDLAS system was deployed within the minutes. It scanned the area in the real time, detected the methane concentrations at the ppm levels, and marked the GPS-tagged hotspot, enabling the fast evacuation and containment before the further risk.
In our system, we implement 5-layer safety architecture that integrates fiber optic sensing with array methane detection for continuous real-time pipeline monitoring. Layer 1 begins with a single-mode optic fiber cables embedded along the underground pipeline. These fibers supports both DAS and DTS that are managed by a single hybrid integrator in Layer 2. The integrator uses a shared laser and fiber port, but it has dedicated detectors and signal board for each subsystem. A narrow line with DFB's lasers generate a stable and coherent beam. This beam is pulsed by an AOM and then boosted using a EDFA to ensure adequate signal strength over the long distance. Before entering the sensing fiber, the light is split by an optical coupler into two paths. The main path injects pulse into the fiber with an optical circulator from port 1 to port 2. Another reference path is used later in coherent signal demodulation. As pulse travel down the fiber, they interact with the environment conditions, which producing both gray light and Raman backscatter. This effectively transforms the fiber into a continuous and distributed acoustic and temperature sensor. The backscatter lights return into the circulator from port 2 to port 3 and entering the detection system. For DAS, we implement coherent OTDR to capture the distributed vibration information along the fiber. The relay signal is coherently mixed with the pre-split reference signal using the heterodyne detection scheme, which enables to preserve both phase and amplitude information. The resulting interference signal is captured by a photodetector, which convert into current and then amplified by a TIA. The analog voltage signal is subsequently digitized by the data acquisition system. The digitized signal undergoes the PGC demodulation, which allows to extract the precise vibration patterns along the fiber. For DTS, the integrator analyzes Raman backscatter, specifically the stroke and anti-stroke component. These are separated by using the filter and detected by two photodetectors. By analyzing the intensity ratio between the anti-stroke and stroke, we compute a distributed temperature profile along the fiber. This allows early detection of leak-induced cooling zones that enable proactive mitigation before hazardous conditions escalate. In Layer 3, signals from both subsystems are processed by an FPGA-based AI decision center. The FPGAs handle the signal demodulation in real time, while the AI engine classifies the pattern that indicates potential threats. If a threat is flagged, Layer 4 autonomously launched a DJI Matrix drone equipped with a Sniper 4D TDLAS sensor. These drones use 1.65 micrometer tunable diode laser and a multi-pass gas cell to perform targeted methane detection. An indium gallium arsenide photodetector measures the light absorption, which allows detection down to 1 ppm methane concentration. The measurement is synchronized with a GPS coordinates and streamed live via the wireless uplink. Finally, in Layer 5, the data is displayed through a cloud-based dashboard by delivering the real-time alerts to the emergency responders, so that the action can be taken effectively from closing the loop from underground sensing to surface-level safety actions. Together, this optoelectronic system architecture enables a passive, accurate, spark-free, and real-time monitoring over a long distance of pipeline. Our implementation plans for 7 phases for the whole PGU pipeline of a 2,693 km, which is set every 50 km per segment. So initially, we will start the implementation of 250 km for the key areas of explosion in Putra Heights. So in the first 4 phases, we follow the flow of planning and vendor selection, fiber trenching and splicing for a passive optical infrastructure to be in place, integrator and AI server setup, and then the drone TDLAS system integration. In phase 5, we will have the calibration and AI training for 4 months to ensure that data accuracy is validated. Then phase 6, a full pilot activation of the first 250 km is implemented. Lastly, in phase 7, the full rollout continues across the remaining 2,373 km of the pipeline. In our project, each 50 km segment costs 8.302 million Malaysian ringgit, which covering the fiber, interrogator, server, and drone system. To protect the full 2,623 kmpgu pipeline, we required a 53 segment with total of capex around 440 million Malaysian ringgit and annual OPEX of 14.3 million Malaysian ringgit. The cost is driven by the trenching and fiber work, but the benefit is national scale and optoelectronic safety that built for the future. Let me first show you 4 optoelectronic solutions already in the market, all built on scattering and absorptions of laser light. For the TDLAS DAS, use very fiber optic laser pulse that phase shift from vibrations, helping spot leak and third-party activity in real time up to 100 kilometers. This challenge here is existing pipeline need to have fiber installed. Every sensing combined DAS with DTS, it detects both vibrations and temperature drop from leaking gas. This low sensing really improves accuracy, but it can struggle in wet or clay rich soil. Visual gas mapping LiDAR use aircraft-mounted laser tuned to methane, creating GPS tag lead map. It is fast and covers large area, though weather and flood limits apply. And finally, the Maverick Laser Falcon, a compact drone-mounted TDLAS sensor. It gives rapid methane reading in dense urban area, but flight range is limited. Globally, demand for this technology is growing fast. The DAS market heading toward $1 billion and DTLS doubling to 4.5 billion. And why does this matter for Malaysia? Many of our aging pipeline run through dense urban zone, right next to ongoing constructions. Combined with our tropical climates, this raises serious risks. To modernize our planet safety, I suggest this path forward. First, deploy DAS at high-risk locations like Putra and use DTLS drone for quick verifications. Next, expand fiber coverage nationwide and set up trained drone team. Finally, by 2028, we bring everything together into an AI-powered dashboard, giving us real-time alert and fast automated response. This will transform how Malaysia manage pipeline safety. But to make this work in Malaysia, we have to tackle some local challenges. Our high humidity and very soil conditions can reduce DAS security. Urban drone flights are restricted. And right now, we lack enough trained operator for DAS, DTLS, and AI system. The solution is we can apply AI adaptive DAS tuned for our climate and combine it with DTS to improve leak detections. We also need to develop safe drone flight corridor with regulators. And just as important, invest in training Malaysian team to operate and maintain the whole system. If we do this, we will ensure reliable detection, flexible coverage, and move forward smart, connected safety network helping to prevent incidents like Putra from happening again.